Hey guys, AP here, and today we are going to be continuing our lightweight Java game library series with another tutorial, obviously. So this tutorial is going to be based off of transformations. Now what transformations are is they're basically translations, rotations, and scaling. So what we have right now is we have the scaling, but we're using one variable. But we can actually simplify this into one matrix. Now we made the matrix in the last one when we made uniforms, but we didn't really add anything to it. We just used it for storage. And now we can actually add stuff to this. And we're also going to add some simple math stuff to the vector classes. But right now we're going to be working on our matrix class. Okay, slight problem. I forgot to actually initialize the list. So this is actually before the tutorial starts, so you see some code. Initialize this array so you don't get this error right here. Of course, if you don't, then you're kind of screwed. Actually, this should be size times size, just so you can keep uniform with that. Anyways, on to the tutorial where you write all this beautiful code. So of course, we have to have 3 new matrices, or 4 new matrices. We first have to have the identity matrix. It's hard to say matrix after saying it so many times. So we have to have the matrix, and I'm just going to make these all static. So matrix, or public static, matrix 4f, and we're going to call this the identity. So what the identity matrix is, it's basically the base matrix, what all matrices are based off of. So what that is it's one diagonal line of ones. So all of them are zeros, and then a diagonal line from 0, 0 to 3, 3 are all ones. So it looks like this. I'm just gonna do it real quick. So 0, 0, 1, 1, and then 0, 1, or 0, 1, 0, and then 0, 0, 0, 1. And then we can add. We could probably put this in comments. So basically, this is what the matrix is. It's 1 in each diagonal. So that's what we're going to be making in this little matrix function, or matrix method. So in the identity method, we need to first of all set them all to 0. So we need to actually initialize it. And so I'm going to create a new matrix, and I'm just going to call it result, and say it's a new matrix. And then we're going to return that result because we have to return a new matrix. And then in between this code, we're actually going to change it. So we need to initialize all the values to 0. So we need to go through it. And since we have a little 2D set in a 1D, in a 1D array with a 2D set, we have to use 2 for loops, or nested for loop. Crap. Stop. Int I equals 0. I is less than size I plus plus, and then we can copy that and change the I to J, 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 and then we can say result dot set I, J, and then the value which is going to be 0. So now all the array, or all the elements in the matrix are set to 0. And then after we set them all to 0, we need to set specific ones to 1, which, as I shown before, it's the ones in the corners. Now, or the ones as a diagonal. So there's a little pattern to those. It's basically I, if we're going off this, I and J are the same. So 0, 0, 1, 1, 2, 2, 3, 3. So what we can do is we can just say result set of 0, 0 is set to 1. And we can do the same for 1, 2, and 3. So result set 1, 2, and 3. Just change the numbers to each respective order. And that is the identity matrix. Like I shown before, it's just a diagonal line of 1, but the rest are 0. So now what we can do with this is we can actually make the rest of our matrices based off this one. So we can just add another one. And this is going to be for translation, so I'm just going to call it translate. It's going to be similar to the identity, except it's actually going to make a translation matrix. So translate, and it's going to be, and the translation is going to be based off a vector. So vector 3f, and then we're just going to call it translate. So we can import our vector, or we don't have to import it because it's in the same package. And then before, we can say matrix for f result, and instead of saying new matrix, we can say matrix for f dot identity, and that would just make the identity matrix, and then now we can return the result. So results, and now what we can do is we can actually use our vector3f information inside our matrix 4f. So I'm just going to show off the matrix real quick. So 1 0 0 x, 0 1 0 y, 0 0 1 z, and then 0 0 0 1. Alright, so this is actually what the matrix stands for. The ones are from the identity matrix like before, but the x, y, and z are from our vector up here. And this is where we're going to insert our x, y, z. So with this is how we're going to make a translation matrix. And how this works for the entire transformation matrix is when we're going to multiply all the matrices together. But we're going to do that at the last step when we actually have all the matrices and all the methods made. So now we're going to work on the translate matrix, and this is how we're going to do it. So the only things we have to change are these three values right here, which is going to be 0 3, 1 3, and 2 3. And this is just the x, y, z respectively. So now what we can say is we can say result dot set, and like I said before, 0 3, and whatever the value is, which is our translate, which is the x value of the translate vector. So now we can do that 3 times for the y and z. So y and z, and instead of saying 0, we can say 1 and 0. Instead of 0, we can say 2. And so that is our translate matrix right there. Pretty simple. And the next one, it's not that simple. So the next one's going to be a rotation matrix. So I'm just going to say rotate. And I'm going to do a different strategy on how I did it at the last tutorial. The last tutorial, I just did it based off another vector. But what I'm going to do now is I'm going to do it based off an angle and axis. So I'm just going to do that real quick. So float angle, and then vector 3f axis. Axes, I don't know. So what the angle is obviously how much you want to rotate it, the matrix or the object in this case, and then the vector 3f axes is how we're going to rotate it. So we can do it based off the x one, which would be a horizontal line, or we can do it a vertical one, which is the y one, or we can do z, which is like forward and backward. But we can also do strange ones like pointed to the right and up, into like pointed to the right all the time, so it's like 45 degrees in every single one, and then you can rotate it based off that axis. Now this one has a bit of complicated math, so I'm going to show you how it is proven. So I'm just going to go to the most trusted source, Wikipedia, to actually show you how to do this. And we could do it based off of these formulas, but we have to make more functions, and I'm just not going to do that. We're just going to do it based off this 3x3, which we can extend to the 4x4. It's not that hard. We just add zeros when there's not one. So yeah, here we go. So we first of all need a few variables. The cosine of theta, which is just the cosine of our angle. We also need the sine of our angle, and so we can actually do that by just creating a few variables in here, saying float cosine is equal to a float, what is it? I don't know. Actually, hold on, let me see what it's called. So math.sine, and then whatever our angle is. So, or angle. We should also make it based off degrees, so we have to convert that to radians. So 2 radians angle. Oh, that's what it's called. It's called a cast. So we have to make a little cast right here to float. I'm just gonna get rid of this for the errors. we also have to make the sign of that. So I'm just going to say sine, and it's going to be the same. Oh, it's going to be cosine here. So there we go. We have the cosine and the sine of the angle in the radians. So that is the first variable. The next one is the inverse of cosine, or whatever that correct term's called. I'm just going to call it the inverse because that's what I think it is. So as you can see, it's actually scattered through this a lot, but you know, it's not that hard to do, except we're just going to make it into a variable. So we can just do cosine, but as a c, and we're just going to do the same thing. Actually, we're not going to do the same thing. We're going to do minus cosine, because that makes it simple, because that's exactly what this is. I know I'm being all over the place, but I'm trying to basically make a rotation matrix from this, and I'm trying to get all the information into there so you understand what each is. If you don't understand, just make a comment below. So that is actually all the information. What these u, x, u at y, u z's, and then u squared and the next, those are basically the unit vector of the axes, which is our axis vector 3f. So now what we can do is actually create our matrix now. So the thing we have to do is we have to use all these set. So there is a total of 9 values ranging from 0, 0 to 3, 3, or 2, 2. So 0, 0, and then the value, I'm just going to put in temporary 1. I'm just going to copy and paste this 8 more times. 1, 2, 3, 4, 5, 6, 7, 8. And so what we can do now is we can say 0 to 2 here. We can add 1 here, 2, or 1, 2, 2, 2, 1, 2, 1. So basically we're just iterating through all this. Now I know I can make a for loop. Actually I can't make a for loop because there's different values for all these, but who cares? So now we actually have to implement all these numbers. So I'm actually going to take you step by step. So cosine plus the x value squared multiplied by the inverse. So we can do that by just saying cosine, because we have a cosine variable, plus the axes vectors, so axes, and then the x value, we have to square that, so times axis dot get x, and then we have to multiply by the inverse, so times c. And so that is the first number. And now we're going to do the next one, which is the x value times the y value times the inverse minus the z value. Why did I say z? Minus the z value times the cosine of it. So axes dot get x times axes dot get y. Oh, I forgot parentheses back here. What was it? Times the inverse minus, I should really write this down, minus the axes of get the z value of the axis multiplied by the sine of it. Now I know this is going to get confusing. It's going to get confusing. Don't worry. So yeah. So next value is kind of similar to it, except you're adding this time, and the x and z, or the z and y are flipped. So you can actually just copy and paste this. So what the boom. So replace the z and the y, and then add instead. So there we go. We got the first row done. It's actually quite similar to this, except you know this is going to be for different ones. It's actually like so similar. I think I could just copy and paste this. That's not what I want. What the heck? And then we could say y. Is that right? Ah, I knew I messed up. Never mind. It goes here. I'm just gonna get this done, and you can just type it in later, or you know, yeah, you can just type it in. I'm not gonna copy and paste it because you gotta work for what you got. And then this is C. I'll be right back. I'll just make a little time lapse. Okay, back. I finally got it all copied. I probably should have prepared this ahead, but I didn't. So here we go. We got the rotation matrix. It has all been tested, as in I looked at it and made sure they're all the same. We can actually see if it works when we get to the end of this. So the last one is going to be the scaling matrix, and it's very easy. It is actually the easiest one out of all of them to understand. So we need another vector 3f because we need a scalar for the x, y, and z. So we're just going to call this a scalar. We can also, if you want to make another one with just a number, you can, but I'm not going to do that because usually, I won't need to. Yeah. So it is actually very similar to the translate, so we can actually copy and paste this, except it has different values. So I'm actually going to make it right here, so it's actually x 0 0 0 0 y 0 0 0 0 z 0 and 0 0 0 1. So this is actually the scaling matrix. Instead of ones for the identity matrix, you just need to replace it with the x, y, and z, and then for the last one, because we don't really use the fourth dimension in graphics programming, you can just put it to 1. So yeah, it's actually very similar to it. We could just replace this with scalar, and we can copy the x1 to the y1, and that is the scaling matrix. So we're almost done with our matrix class for this tutorial. We have our 4 new matrices, and now we need a way to multiply all these matrices. So we're actually going to create a static method for this one where we're just going to plug in 2 matrices so they don't change the matrix, and we're going to return a new one. So matrix for f, and we're going to call this multiply. And like I said, we're going to put in 2 matrix, so this is going to be just matrix, and then the other one's just going to be called other, just for lack of a better term. And we're going to do the same thing we have for the other ones, make identity matrix and then return it. But now we actually need to do some for loop. So how do we multiply a matrix? Well, it's kind of complicated. I can try to explain it, but then I'll make you guys more confused. So what I'd usually do is I just make it and then set it aside, knowing that it works, sort of without knowing how it works, which is good if you're just starting out, but once you get later on down the road, it's not good if you know what it is. I sort of know what it is, but I can't really explain it because I don't really know that well. Think of it like a black box. You know it works, you just don't know how it works. So let's actually get started. So the first thing we need to do is we need to actually go through the entire matrix, the result matrix. So we can do that similarly to how we did the identity matrix with these 2 ones. In fact, we're just going to copy and paste it down here. So we're going to put that back down there. So instead of setting it to 0, we are actually going to set it to a little formula where it multiplies the entire row in the column. So what that means is, I really can't, like I said, I can't explain it, but I know it works. So the first thing we need to do is we need to get the matrix, this matrix, the first one, and we need to get the first index, or we need to get the row this one's currently on by the first index, and then we need to multiply it by the other matrix where it gets the column and it gets the first index of the column. So we can do that by doing that. So then after we do that, we have to do the same thing but for the rest of the row, and we add those all together to get what the first one, and then it goes through the next one, and it goes to the next one. Add a plus sign there, and there we go. So all we have to do is change this to 1, 2, 3, and that's how we multiply a matrix. I know it's a bit confusing. If you want to look it up, just look it up. Maybe Khan Academy might have a good one. I don't know. Maybe Wikipedia again might have a good one. YouTube's a really good source for this, just not this YouTube video. But yeah, now that we have all of our functions for this tutorial in, we can actually use those. So next thing we got to do is we got to make a way to actually use these things, these functions, to go into the graphics, the shaders. So before, there it is. Before, we actually used just one float to set the scale, but now we can use an entire matrix, and not only that, we can multiply all these matrices together to pass it through at once, and that's it. They're all going to work together to make the final product. However, we don't have any way to store it. We have ourselves some rendering data, but I don't want to put this in here because it makes no sense. Why would that be in there? So to actually do this, I'm going to create another package in our engine called objects. And what objects are going to be is basically going to be the crutch of our engine. It's going to be what's actually going to be on the screen. It's going to be, I actually made a class. It's going to be what's going to be on the screen and what we are going to control, basically. So package objects. That should be in our engine. So engine.objects. Object will do. I'm tired of messing with it. Actually, you know what? You guys probably are ahead of me because, you know, this is giving me a tough time. But okay, so in our object, we are actually going to create a game object. So this is going to be basically what all of our programming is going to in the later tutorials once we get done with all these graphic things. So with this game object, we need, well, 4 things. We need the translation, rotation, and scaling vectors. So public, or not even public, we're going to do private vector 3f or position, rotation, and scale. With that, we need to actually import vector 3f, save and then import it. We're going to use engine maths, and then we're going to have a mesh, you know, to actually see what object it is. Or you can just put in no mesh at all, it's fine. So with this mesh, we're going to import it. What we're going to do is we're actually going to do something similar to like the generated getters and setters. We're actually going to generate a constructor using these variables. I just had a brain fart for some reason. We don't need the super because this doesn't have a class that we use it on. This will probably be a parent for all the objects we have. But yeah, so now what we can do is we also get getters because we don't really need setters. So generate getters and setters, select getters, and there we go. That is going to be our game objects done. What we're actually going to do is we're also going to have an update, so we can actually update it. This is going to be temporarily so I can show you that these matrices are working, and this is when we're actually going to use some math for our vectors. And they're not hard math, it's just going to be one function, which is going to be called add, because you need an add function for most of these. So public void add, and it's just going to have an x and y, so float x or float y and float z. And then what we can do is say this dot x is plus equals x, this dot y plus equals y, and this dot z plus equals z. We could probably just make this a static like we did matrix, and I am probably going to do that. It's just right now, this is very temporary just to show you that it's working. So now that we have our game object, we can actually put this in our shader. Just to make sure it's working, I'm just going to say position dot add 0.100. This should be f. Alright, so now that we have our position.add, we can actually import this into our shaders. So before, we are using scale. We're probably going to change it in here first. So uniform mat4, which is matrix in our shader language, and we're actually going to call this model. What model is, it's basically a transformation matrix, but I'm just going to call it a model for the MVP, which I'll explain in the next tutorial, which stands for model view projection or perspective, or whatever you like to call it. There's a lot of different names for these, but they all mean the same thing. So now what we can do, instead of multiplying by this vec4, we can just say multiply by the model. And that is it for our shaders. We do not need to mess with these shaders anymore, but in our renderer we need to set our model uniform to something. So what we need to do is we need to multiply all the matrices together. I'm just going to make a helper function in the matrix 4f to do that, because doing all that in this one little function right here is going to be a lot. So I'm actually going to do it where the math is already there. So after we have all this, I'm just going to put it right under here, and I'm just going to say public static matrix 4f transform. And it's going to take in the 3 vectors that we had in our game object. So position, vector 3f rotation, and vector 3f scaling. Or just scale, we don't even need that. So now what we can do with this transform is we can actually make that into a transformation matrix. So like always, we need a result and a return result, but of course our metals are going to be different. We're actually going to multiply this result by other matrices. So the first matrix is going to be called actually we can just say matrix 4f dot multiply result and other. Actually, so to actually start this, we need to make 5 matrices. The first one is going to be the translation matrix. So I'm just going to call it that, and I'm just going to set that equal to the translation matrix math that we did up here. So translate, and we're going to translate it by the position, not the rotation, position. And the next 3 are going to be the rotation matrices. So we're going to have a rotation X matrix, and if you remember before, we need to rotate it by the angle and the axes. So rotate by the angle, which is our rotation, the X component of it, so rotation.getX. The axes, which is going to be the x-axis, which is a vector, which is going to only have the x be a 1. This, by the way, this axis has to be a unit vector, which means it has a length of 1. So putting 1 in only one of these will work, but if it's longer than 1, it will mess up. So the next thing we gotta do is we also have to have a rotation matrix for the other 2. So similarly, you get what I mean. Whatever. Similarly to the other ones, we have to say get y, and then for the y-axis, and then get z, and for the z-axis. I don't want to say z. I'm not British. And then for the final matrix, we are going to have the scale matrix, which is similar to the translation. All we have to do is call scale, and we just call it by scale. And now we have to multiply all these matrices. And so what we should do is we should first make a rotation, like the entire rotation matrix, by saying matrix 4f rotation matrix is equal to matrix.4f dot multiply the rot x matrix by another matrix multiplication, so matrix multiply by, which is the rot y and the rot z. And that is our entire rotation matrix multiplied. And so finally we can set result, the final result of all this, to all of them multiplied together. So it's actually similar to how we multiplied here. So we can just copy here and then replace all these with these new ones. And with this final matrix, that is our transformation class complete. So all we have to do is import all of what our game object is, and we can just make ourselves a transformation matrix. So now in our renderer, we can say matrix for f dot transform, and since we have ourselves a mesh and not a game object, we should actually change that. So game object, if I can make that all frick there. So I'm just going to call this object. Now we're going to get a bunch of errors in other locations, but for right now it's fine. We can just say object dot get position, object dot get rotation, and object dot get scale. So now we have ourselves the uniform working, but now as you can see, mesh is not working. However, our object does have a get mesh, so we can copy and paste that to where mesh was. So now our renderer should be complete. Oh, we also don't need temp anymore because we're not uploading that every frame. So the next thing we gotta do is we actually have to fix our main program. As you can see, we're still rendering with a mesh. We should not do that. We should instead use a game object. So public game object, I'm just going to call it an object, and we're going to set this to equal to a new game object, which is equal to the mesh we entered, and then the new vectors. So new vector 3f, we are going to just say 0, 0, 0, and that's just going to be the same for the rest of them, except for the scale, because scaling starts at 1. If you make it 0, it disappears. So now import game object. Oh wait, mesh is not first. That probably shouldn't be what happens, but whatever. So now, instead of saying render mesh, we could just say render the object. We probably should change the name, but I'm too lazy to anyways. So what should happen is nothing. So now if we run this, we should get ourselves a beautiful nothing different. Like I said, nothing should be different. You should still get the same rectangle, because we haven't really put anything different for these values. However, if we go into our update, we call object dot update, which is down here, because of our adding to our position, we should see, oh, and it's gone. That is way too fast. But you see it move. So I'm actually going to turn that down just a tiny bit. We're also going to change everything that to where it's actually based off another thing, temp. the beautiful temp, so private double temp. And then every frame we add temp, so plus equals 0.02. We set the position, so we can actually just say position dot set to this, and we can say actually we should just say set x, because y will make it go crazy, and there's no such thing as a z right now. So this should be casted to float math dot sign of temp. And so with that, we can also say that the rotation, and we're actually going to set this rotation to all of them, because that makes sense. Let me just put all of you in there. We also have to multiply this by 360 degrees, because going from 0 to 1 using a degree is kind of weird. So we're just going to use 360 degrees. And then finally we can say rotation or scale dot set, and similarly to this one, we're going to put this in here, except not 360 because that's too big. Probably like 2, because actually let's not put anything because I don't want it to take up the entire screen. Alright, so using some cool math, we can make ourselves a cool flat plane, basically. Let's see this go crazy. Oh, heck yeah, look at that go. Woo! Now, if you've seen it before, you can see that this really does not look correct. Because it's sometimes turning into a square, and it's sometimes turning into a rectangle. However, like I said, it should always be a square, and it's not a square. So in the next tutorial, we're actually going to be making this look correctly with a projection matrix, and maybe add a view matrix and a camera later on, like a temporary camera, and then later on we can actually make it a concrete camera. So anyways, that's the end of this tutorial. It's a bit of a long one. It's about almost 40-50 minutes, I think. I don't know how long it is, but it's a pretty long one. I'm sorry if you didn't stay through it. I'm sorry if it's too long for you. I went rambling on, but it's cool. Like the tutorial, please like it. If you want to see more of these tutorials, please subscribe, and I'll see you guys in the next tutorial. Bye!